Hello there, Mr. Sutton here with the AB Calculus 611 Extra Practice Number 1 solutions on accumulation and rate in, rate out free response practice. For this problem, we have a twice differentiable function W modeling the volume of water in a reservoir at time t, and this is in gigaliters and t is in days. We have a table of values of W prime. So we're told at time 30 the reservoir contains 125 gigaliters of water. Good to know. All right, so we're going to use a tangent line approximation at time 30, which they already gave us a value for, to predict the volume of water at time 32. So my general setup for this that I'm going to write down first, and I normally never just write general formulas, but this one I always do. I'm going to use my tangent line approximation formula, W of x equals f of a plus f prime of a times x minus a. I just like writing it all out so that I have my shopping list of things I need to find. Now applying that to this problem, a in this case is going to be 30 because that's what our tangent line approximation is launching off of. So I can say that W prime of t is approximately equal to W of 30 plus W prime of 30 times x minus 30. And in this case, I'll have a t minus 30 because we're using t as our input variable here. All right, so let's fill in each of these things. W of 30, what's that going to be? Well, that's going to be the 125 they said was our gigaliters at time 30. And W prime of 30. Well, we have a table of values of W prime. Up here, when I plug in 30, I get a W prime of 0.5. And let me backtrack a little bit. I'm actually going to say W of 32 is approximately equal to these things because I'm actually about to plug in 32 for t now. So in my parentheses, now I've got 32 minus 30. And I could just leave it like this and put units on and be done with it. But if we want to simplify this, I mean 32 minus 30, that's 2. Half of that is 1. 125 plus 1 is 126. And we were approximating the number of gigaliters, so I'll call this GLs. On this problem, they want us to use a left Riemann sum with 3 subintervals, indicated by this table, to approximate the integral of W primes from 0 to 30. And then we'll use that for some other stuff in a minute, but let's do this part first. So I can say W prime of t integral from 0 to 30 is approximately equal to, and I have to write approximately because I'm not finding the actual value. So I'm going to do left Riemann sum. So I have a bunch of base times height rectangles that I'm adding together. My first base from 0 to 10 is a base of 10 times a height of, let's see, do I do 0.6 or 0.7? Well, it's a left Riemann sum, so I'm going to take the left side here, 0.6. Then I'm going to do a base of 12 times a height of 0.7. And finally, a base of 8 from 22 to 30 times my height of 1. And then if I wanted to add all these together, I don't have to. I can just stick units on the end. But it would probably help if I'm going to use it for something later on. I've got, let's see, this is 6 plus, well, 12 times 7 would be 84. So this would be 8.4. And then this is going to be just 8. So let me see here. That's going to be 6 and 8 is 14, plus another 8.4 is 22.4, and that's gigaliters, because we're integrating a rate of change of gigaliters. Now for the next part of the problem. Use this approximation to estimate, so we still have to say approximately equals to, estimate the volume of water in gigaliters in the reservoir at time 0. So to get time 0, we already know the gigaliters at time 30. So we're going to use our FTC and kind of go backwards to figure out time 0. So I can say W of 0 equals, and actually let me make that approximately equals. Although, no, actually not yet. I'll save the approximation for later. So this equals is exactly equal to 125. And then if I want to go backwards from 30, which is, this is W of 30 right here, to 0, I have to subtract the integral from 0 to 30 of W prime of t dt. Okay, now the problem is I don't know the exact value of this integral, so now I'm going to write that W of 0 is approximately equal to 125 minus our approximation of W prime integral right here, 22.4. And this is going to come out to, let's see here, that's going to be 125 minus 22 would just be 103, subtracting another 0.4, so that's 102.6 gigaliters. For part C, they want us to explain why there's at least one time other than time equals 10 where we have a W prime value of 0.7. So one other time other than this. Well, looking along my table here, I see that I'm moving from 1.0 to 0.5 on the interval from 22 to 30. So there's probably a 0.7 in there. But to prove it, we're going to need to use the intermediate value theorem on W prime. And to do that, we're going to need to show that W prime is continuous. The key on this is they told us W was twice differentiable. And this is important that it's twice differentiable, because the fact that W is differentiable by itself does not prove W prime is continuous. It just proves that the limit exists everywhere for W prime. So to get the continuity, the fact that W is twice differentiable, that means that W prime itself is differentiable, and that is enough to show that W prime is also continuous. So that means we can use the intermediate value theorem. So we see here that the value we're looking for, 0.7, is between W prime of 22 and W prime of 30. In fact, it goes the other direction because W prime of 30 is less. And just to write in the numbers here, we have 0.5 less than 0.7 less than 1.0. So therefore, by the intermediate value theorem, we know that W prime equals 0.7 somewhere on the interval from 22 to 30. For this last part of the problem, they're giving us the equation A equals 0.3W to the 2/3, which is a relationship between the surface area of the water, which is A, and the volume of the water that they already gave us, which is W. So we want to find the instantaneous rate of change of A with respect to T at 30 days. Well, if I want the IROC for A, I'm going to need a derivative. The catch on this is that A and W are both functions of time, and they wanted the rate of change with respect to time, with respect to T. So we can't just take the derivative here in terms of W. We're going to have to use related rates and differentiate all of this with a dt tail here. So A, that derivative is going to be dA over dt. And on the right side, using our power rule, 2/3 times 0.3 is 0.2. So this is 0.2W to the negative 1/3. But we also have a dW over dt tail on the right side, because again, A and W are both functions of time. Now to find dA over dt, we just need things to plug in for W and dW over dt. So keep in mind that these are both quantities that only apply when T equals 30. So we're going to use that fact to figure out what these both are. W, for example, they're talking about the value of W at time 30. They gave us that in the beginning of the problem up here where they said at time 30, the reservoir contains 125 gigaliters. So 125 is the value of W when time equals 30. And then for dW over dt, this is essentially W prime of 30, which they gave us in the table up here. That's 0.5. Plug in all this in. We've got 0.2 times 125 to the negative 1/3 times 0.5. And you could actually just put the units, kilometers squared per day on the end. And then this problem would be done. But if you chose to simplify it, we could rewrite this 125 here as, let's see, this will be cube root of 125 in the denominator. And then, let's see, the cube root of 125 is 5. 0.5 over 5 is going to be 0.1. And if we multiply that by 2, that's going to be 0.02. So 0.02 kilometers squared per day. For this problem, the temperature outside a house during a 24-hour period is given by this f of t function, where this is in Fahrenheit. And we want to sketch the graph of f on the grid below for part A. So there's no real tricks here. This is just, hey, graph this trig function. And this was also a calculator problem, so you could have used that to help you out. But you might not need a calculator if you remember your trig graphing from pre-calculus days. So looking at our quantities here that are going to be helpful for graphing this, we have a k value of 80. That gives us the midline, the vertical middle of the graph, which, hey, surprise, is the vertical middle of the grid they gave us. Nice. Next, we have an amplitude of this 10 right here. That tells us how much we're going up and down from 80 to get the cosine wave. So we're going between 70 and 90 vertically. And then the last important piece on this one, the period, that's going to be 2 pi divided by this pi over 12 coefficient on t here. So that's 24 if you do same change flip. And that tells us how long it takes for the whole cycle to repeat. So we're using cosine, negative cosine. That means my very first thing I need to do is go down the amplitude from the midline. So I'm starting down at 70 here. And this is my first dot. Now cosine is going to go up from there. How far over do we have to go before we go up one of these amplitudes? Well, we always split the period up into 4 pieces to get each part of the wave. 24 divided by 4 gives us 6. So we're going by 6s, which, as luck would have it, is exactly the grid lines they gave us. So we're going up to 80, and then we're going up one more time to the top of this cosine wave, then back down to 80, down another amplitude to 70, and just graph a smooth cosine curve with some nice concavity changes at these at the midline here. There we go. For part B, they want the average temperature to the nearest Fahrenheit degree between times 6 and 14. So the setup for this, we're just going to do 1 over b minus a times the integral from a to b of whatever we're averaging. In this case, since we're going from 6 to 14, we're doing 1 over 14 minus 6. So that gives us the interval length. That's essentially what you're dividing by to get your average. And we have the integral from 6 to 14 of, well, what are we trying to average here? The Fahrenheit. So let's just plug this f of t inside my integrand. So f of t dt. But now I have to do this on the calculator. To make my life a little bit less hectic with trying to put this inside an integral, I'm going to put this inside y equals the y1. And then let me quit out of there, and let me put all of this in my calculator now. So let's see, I've got alpha y equals, to get my fancy fraction here, 1 over, and I know 14 minus 6 is 8, but I'm just going to put it in there anyway because, hey, why take chances when I can just use the calculator? We're going from 6 to 14 on my integral, which I got with Math 9, and then alpha trace to get y1 in there, and then let me do dx over here. And they wanted the nearest degree, so that's going to be 87 degrees Fahrenheit. For part C, and they said an air conditioner cools the house whenever the outside temperature is at or above 78 degrees Fahrenheit. So for what values of t is the air conditioner cooling the house? So for this one, we need to figure out when this f of t function equals 78. And I'm going to do this on the calculator, and then whatever interval gives us that's above that 78 or equal to it, that's going to be when our air conditioner is cooling the house. So let me go back to the grapher. Now, again, I've stored my f of t function in my y1. I'm going to graph this now. I'm going to first go to window, though, and change my window. I want this to be from, let's see, what's a good interval here? How about 0 to 24? So let's put that in, 0 to 24. And then let me do zoom fit, zoom 0. And here's my graph. But I am missing one key piece here. I need to know when this equals 78. So to figure that out, I'm going to go back to y equals, and I'm actually going to graph y equals 78 here in my y2. Now let me do zoom fit again and see if I get a slightly different looking picture. So there is my original f of t function. Here is 78, and I just have to find out the intersection of these. So I'm going to do second trace intersect, option 5. And then let's see here. I'm going to move my spider closer to the intersection that I want. And then I'm going to press enter 3 times. So 1, 2, 3. And we get this intersection at 5.2309. I'm actually going to quit out for a second and store that as A. I'm going to do the store button here and do alpha A so that in case I need that value again, I can pull it back. I'm also, on my paper here, going to let that value equal A so that whenever I write A on my written work, I can get credit for having this number here. Let me go back to the grapher now and get the other intersection point. So let me do second trace again, intersect again, option 5. And now I'm going to move closer to this other intersection point with my little spider here. All right, there we go. And now let me press enter 3 times. And that gives us the value 18.769 if I round that off. Just like what I did with the other one, I'm going to quit out, and I'm going to store that as alpha something else. I'm going to do alpha b this time around. And I'll do the exact same thing on my paper. I'm going to write that I'm basically calling this value b. All right, now. So for this part of the problem, we just wanted to know when the air conditioner was cooling the house. We observe that f of t is greater than or equal to 78 on the interval from A to B. And this is really nice because I don't have to rewrite these numbers now. So that means my conclusion then is that the air conditioner is cooling our house on that interval. For the last part of this problem, we've got kind of a real-life application of all this stuff. The cost of cooling the house accumulates at the rate of $0.05 per hour, so 5 cents an hour. For each degree, the outside temperature exceeds 78 degrees Fahrenheit. We want the total cost to cool the house over the 24-hour period. Okay, so if I want to add up the total cost, I essentially need an integral, but it'd be nice if I had a function to kind of represent how much I'm going to pay at each moment in time. Well, they said that we're paying 5 cents an hour for each degree that the outside temperature exceeds 78 degrees Fahrenheit. So if I write f of t minus 78, that's going to tell me how far over I am on the 78 degrees. So in order to add all of these different little slices of degree overages up, we're going to need, first off, I'll put the 0.05 out in front, and I'm going to need an integral from, well, the first time that the air conditioner kicks on to the time it kicks off. Now, you might remember from part C that the air conditioner only turns on when we are at or above 78 degrees. Do we know what time interval we are at or above 78 degrees? Well, yeah, we do. We found that in part C. And I wisely stored my values, my time values, as A and B. So I'm just going to do the integral from A to B because I've defined those in part C. And just looking back real quick, A was about 5 and some change. B was around 18 or 19 hours. But I've already stored those, so I don't have to rewrite them. Lucky me. And then I'm going to go ahead and put a function in here. This is going to be f of t minus 78. Again, this is the how far I am over part of this function. And I'll have a dt in there as well. So all I have to do now is go on the calculator and plug this in. So I'm going to have 0.05 times an integral, so math 9. And I'm going to do alpha a for the lower limit, and then I'm going to do alpha b for that upper limit. Inside, I already stored my f of t as y1, so I'm going to do alpha trace y1 minus 78 to add all those up, and I'll put a dx over here. And let's see what it comes out to. So they wanted this rounded to the nearest cent, so this would be $5, and let's see, this goes up to a 10, so $5.10. For this problem, we have a store having a 12-hour sale. Woohoo! Total number of shoppers who have entered the store T hours after the sale is modeled by the S function, defined as follows right here. So we want to know, so at time 0, they're also telling us when the sale begins, there are no shoppers in the store. Because, I mean, that would be kind of creepy. How did they get in the store before the sale began? All right, so for part A, at what rate are shoppers entering the store 3 hours after the start of the sale? Well, the number of shoppers is defined by S, so the rate at which they are entering is going to be S prime of t, and this is going to be S prime of 3. We're going to go ahead now and calculate this on the calculator. Now, before I actually do anything else on the calculator, I'm immediately going to go to y equals in y1 and store this little function because I have a feeling I'm going to need this multiple times for this free response problem. Now let me just differentiate that at 3. So math 8, I'll do a dx down there. In here, I'm now going to put alpha trace y1 because that's where I stored my s function. And I want to differentiate that at x equals 3. And this gives us a value of, let's see here, about 486. We're going to have to round it off to 86. And that is going to be shoppers per hour. For part B, they want us to find the value of 1/3 times the integral from 6 to 9 of s prime of t dt. And then we'll do some other stuff at the end where we explain what it actually means. But let's actually find the value first. Now, there's a few ways to do this. You know the antiderivative of s prime of t. It's just s, which is up here. So you could just do 1/3 times s of 9 minus s of 6, and that would get you an answer. But I'm going to kind of sort of take the long way around and define s prime of t and then use it in here. And the reason I'm doing this is I've kind of looked ahead on this problem, and I've seen that I'm going to need to know have a function predefined for the rate of change of s. So I'm just going to do it now and get it over with, as it were. So s prime, that's going to be, let's see, using my power rule, this is going to be 2t cubed, and then this is negative 48t squared, followed by, this is 288t. All right, so now I'm going to actually put this in my calculator. I'm going to put this in y2. So I've stored this in y2, and then I'm going to quit out of there, and I'm just going to enter this expression now. So let's see, Francie fraction, whoops, that's not what I wanted. Go back. Alpha y equals, there we go, n over d, 1/3 for my fraction. And then math 9, I have an integral from, they said, 6 to 9. And I'm going to do alpha trace y2 because that's where I stored my s prime in the calculator. And we'll dx this one. Equals 301.5. Okay, sure, I'll take your word for it, calculator. But now here's the part where I can't just rely on the calculator. Using correct units, explain the meaning of this thing that you just found in the context of the problem. So you might have to look at this a little bit to see what's happening. They kind of hid some information here. This was really 1 over 9 minus 6 times the integral from 6 to 9 of s prime of t dt. So this is an average value that's happening. This is the setup for average value. What are we averaging? Well, s prime, if s is the number of shoppers who have entered the store, s prime is the rate at which shoppers are entering. So I'm averaging the rate and getting the average rate at which shoppers are entering the store. Now, what is this going to be measured in? Well, it's going to have the same units as shopper entering rate, which is just shoppers per hour. And we also have to include the time interval on all these explain the meaning of kind of questions. So this is happening between 6 and 9 hours. For part C, the rate at which shoppers leave the store because they have to go home at some point is modeled by this L of t function. So S prime is the rate in, L of t is the rate out. According to the model, how many shoppers are in the store at the end of the sale, time 12? And then give the answer to the nearest whole number. All right, so we need a function that tells us the total number of shoppers in the store at any given time. S doesn't quite do it. S tells us how many shoppers have entered the store after t hours, but it does not account for the shoppers who leave. So we're going to define n of t as the number of shoppers in the store. And we don't have an expression for this quite yet, but we can write an expression for n prime of t, the rate at which the number of shoppers in the store is changing. N prime of t is going to be the rate at which they're entering, which is s prime of t, minus the rate at which they're leaving, which is L of t. So s prime minus L, that'll be our n prime function that tells us the rate at which the shoppers are changing. Now, to actually figure out the number of shoppers in the store, we can use the fundamental theorem of calculus. So we have our initial value. They said at time 0, there were no shoppers in the store, so we're starting with a value of 0, and we're adding to that the integral from 0 to 12 of this n prime function. So we're starting with 0, adding an integral from 0 to 12 of n prime of t dt, and now I'm going to actually have to plug this in the calculator. So I know this next step will come as a shock, but to make my life easier, I'm going to put L of t in as one of my y equals functions, y3 in this case, and then I'm going to go down to y4 because this is what I really need here, and I'm going to enter this n prime function. So that's going to be s prime, which we stored here in y2, so alpha trace y2, I'm glad I stored that from earlier, minus alpha trace y3 to get my L of t function. There we go. All right, let me quit out of this now. And I don't need to bother writing 0, but I do need the integral, so math 9, integral from 0 to 12 of alpha trace y4, where I've stored my n prime function. And then I'll dx this thing, press enter, and we wanted to round it to the nearest shopper. So at the end of the sale, there are 196 shoppers still in the store. For the last part of this free response, using our models that we've done from before, on the interval from 0 to 12, we want to know when the number of shoppers is the greatest. So we're trying to maximize the n of t function that we defined in part C that told us the number of people in the store? Well, we know we're going to have to test the endpoints, 0 and 12. This is our candidates test we're about to do. But we also need to find some critical values to test in between here. So I'm going to let n prime of t equal 0. And now let me graph this out on the calculator. So just a reminder from part C that I stored this n prime function, which is really s prime minus L of t, as this y4 function. I am going to deselect all my other y equals because I don't want to graph 4 things on the calculator. Just one is enough. So just this n prime function. And what's my window going to be? Well, I care about the interval from 0 to 12. So let me go to Window, and I'll change this to 0 to 12. And let me zoom fit this thing. So pressing zoom 0, here is what our function looks like on the interval from 0 to 12. And we see that there is just one critical value here. So let me go ahead and find that. I'll do second trace, 0. And let me move a little bit to the left, press enter, a little bit to the right, press enter, enter one more time, and we get about 5.545. I'm going to quit out of here immediately and store that value. So I'm just going to store this as alpha A. And now I can pull that value back whenever I want. Okay, so here's what I just did on the calculator. And I'm going to write up here that this is true at t equals A equals 5 and change here. And now I don't have to keep rewriting this number. I can just write A instead because I've defined it that way. So now it's time for our candidates test. We have the 2 endpoints and this one lone critical value in here. So doing our candidates test, we've got n of 0. That's the number of shoppers in the store when the sale begins. We know that was 0. They told us in the beginning of the problem. Now let me do n of A, I guess I'm doing. That's going to be this amount of 0 plus the integral from 0 to A of n prime of t dt. So let me do that on the calculator. So I have integral, math 9, from 0 to alpha A. And again, I stored n prime as y4, so alpha trace y4 dx. And that comes out to approximately 1,362 shoppers-ish. All right. And then we have n of 12, which we actually found in part C was 196. So out of all of these, 1,362 is by far the biggest. So we can say that the number of shoppers is at a maximum at time equals A hours. So this was one way to do the problem. If you didn't want to use the candidates test, you could have simply said that n prime was greater than 0 on the interval from 0 to A, and n prime was less than 0 on the interval from A to 12. Therefore, because n is increasing until this point and decreasing afterwards, A hours had to be the highest point. Just another way to look at it.